Hi, thanks for joining me. Today I'm going to be talking a little bit about differentiability. So this is if you've just been introduced to differentiation. At least when I was first introduced to differentiation, all the functions that you meet are nice, smooth, infinitely differentiable functions, sine x, cosine x, polynomials, log x, when x is positive, and that sort of stuff. But not all functions are nice and differentiable, and today we're going to explore them. Perhaps the first function that you'll ever meet, which is not differentiable, will be something like modulus of x. And that's going to be the inspiration for today's video. We're going to be using the modulus of x and adapting it to find a function which is exactly n times differentiable, where n is any natural number you want. So you can differentiate it n times, but then if you try and differentiate it again, you're going to mess up somewhere. Okay, it won't be differentiable, at least at one point, when you try and do it n plus 1 times. Okay, so if you want to try and find some functions yourself, pause the video now and give it a go for yourself, but I'm just going to get stuck in. Okay, so in my intro I talked about the modulus of x. Let's quickly go over it if you haven't seen it before. So we denote it with these sort of two lines next to the x. Y equals the modulus of x. And this is its graph. So if this is my xy plane, this graph here is y equals modulus of x. So it takes the value x when x is non-negative, and it takes the value minus x when x is negative. And it makes this function here always non-negative. Okay, now if we work out its derivative, if we look for any positive x, this thing here is just going to look like the straight line y equals x. So the derivative here in this, let me write it here, y prime is going to be equal to 1 if x is bigger than 0, and it's going to be equal to minus 1 if x is less than 0. Okay, because obviously when x is less than 0, this thing here looks like minus x. So obviously the derivative of that is minus 1, and similarly when x is positive, it looks like x, and the derivative of x is just 1. However, we don't define the derivative at 0, and that's because the derivative at 0 doesn't exist, because for the derivative to exist at 0, sort of the limit as you go from either side, so either the positive side and the negative side, they should be the same. Obviously 1 doesn't equal minus 1, so the derivative at 0 of the modulus of x doesn't exist. Okay, so this is an example of a function which isn't differentiable. It's differentiable everywhere except the origin, but because there's at least one point where it's not differentiable, we say that the function is not differentiable. Okay, now what we want to do is sort of use the modulus of x to find a function which is n times differentiable, but not n plus 1 times differentiable. Okay, so let's look at the case where n equals 1 first, then we'll look at n equals 2, and then you'll see it's quite easy to generalise to any n. Now, of course, this is just one particular solution, and there will be loads and loads of different solutions, but this is essentially to use the modulus of x, and using properties of the modulus of x to find a solution. Okay, so we want a function which we can differentiate once, but we can't differentiate twice. Now, we just showed that the modulus of x is not differentiable at 0, and thus not a differentiable function. So if we can find a function which differentiates to give us the modulus of x, then we'll know it's differentiable once, because we get to the modulus of x, but then we know it's not going to be differentiable twice, because if we try and differentiate it twice, we're going to try and differentiate the modulus function, which we know isn't differentiable. Okay, so essentially we're trying to integrate the modulus function, and that's not too difficult to do. Remember, y equals modulus of x is defined to be x if x is bigger than or equal to 0, and minus x if x is less than or equal to 0, or I'll just say less than 0. Okay, so if we want to integrate y, because remember integration and differentiation are sort of like opposite operators, let's integrate y to give us the case n equals 1. We'll call it y tilde. So when we integrate x, we get half x squared, and we're going to ignore this constant term. So that's for x greater than or equal to 0, and then when we integrate minus x, we get minus a half x squared, and that's for x less than 0. Now let's check that y tilde is differentiable once, but not differentiable twice. Okay, so firstly, let's quickly draw a sketch of y tilde. Okay, so it's half x squared when x is non-negative, so it's going to look something like this. And then when x is negative, it's going to be minus a half x squared. So it's going to look something like this. Okay, let's check that it's differentiable. Well, it's clearly differentiable for x positive and x negative, because x squared and minus x squared are nice and differentiable functions. we only need to check that it's differentiable at the origin. So we've got to check as x is positive and getting closer and closer to 0, does y tilde approach the same limit as when we look at x negative approaching 0. Okay, so what I'm going to call this is y tilde prime 0 plus. So to denote the derivative of y tilde as we approach from the positive reals, so we're going essentially along this line here. Okay, well, what's the derivative of y tilde? Well, it's just x for positive x. So half x squared, derivative of that is just x, and we're evaluating it 0 plus. So of course that's going to be equal to 0 as we get closer and closer to 0. And a similar sort of thing for negative. So if I look at the derivative of y for negative x, it's going to equal minus x, but we're evaluating that at 0, so we're still going to get 0. Okay, so I've shown that the derivative at 0 exists because when I look at it from the positive side and the negative side, I get the same number, in this case 0. Okay, so that means that y tilde is a nice and differentiable function, and we know that it differentiates to the modulus function, which we know isn't differentiable. Okay, so we found a function, which I've called y tilde, which is differentiable precisely once. Okay, now we're going to essentially use the same strategy to work out the case n equals 2, and then hopefully from that you'll be able to see a very general case of n. Okay, so now we're going to focus on the case where n equals 2, so we want to find a function which is twice differentiable but not 3 times differentiable. Okay, so we just showed that y tilde was once differentiable but not twice differentiable. So if we can find a function which differentiates to give us y tilde, same sort of thing, so if we can find a y, say double tilde, which differentiates to give me y tilde, then I know it's differentiable once to give me y tilde, and then I know y tilde is differentiable exactly once, so that will mean that y double tilde is differentiable exactly twice. So to work out what a y tilde, we're just going to integrate y tilde. Okay, so a lot of y's and a lot of tildes there, but let's just have y double tilde to be the integral of this thing here. So the integral of half x squared is going to be a sixth x cubed, and that's for x bigger than or equal to 0, and minus a sixth x cubed for x less than 0. Okay, and I'll leave the details to you, but you can check this thing here is differentiable. It's very clear that it's differentiable for positive x and negative x, but obviously you've just got to check at the origin, is it differentiable? And again, it will come down to the same thing. When you differentiate this and plug in 0, you're going to get 0 both times, so it's differentiable at the origin, and clearly the derivative of this is y tilde, because we just worked this out by integrating y tilde, and integration and differentiation are sort of opposites. Okay, so we found an example in the case n equals 2, and in fact we can just generalize this. Notice at the bottom here was 2 factorial, here was 3 factorial, so if I call y mx will equal 1 over n plus 1 factorial times x to the n plus 1 if x is bigger than or equal to 0, and minus x to the n plus 1 if x is less than 0. This thing here is an n times differentiable function, but not an n plus 1 times differentiable function. So that sort of solves the problem. And in fact, I've written out this 1 over n plus 1 factorial here. We don't actually need that. That's just a constant of integration. So I might as well just sort of multiply through by n plus 1 factorial. So the coefficient is just 1. So I get yn of x is equal to this thing here. And you can check this is differentiable n times, but it's not differentiable n plus 1 times, because when you try and differentiate it n plus 1 times, once you differentiate it n times, you're going to be left with a modulus function, which we know isn't differentiable. And of course, as I said, this is just one particular example of a function which is only n times differentiable, but I thought I'd make this video just to introduce people who haven't come across non-differentiable functions, just that they exist. Don't be scared of them. They do exist, but you've got to be aware that they exist. Anyway, I hope you have enjoyed this video. If you are new here, please do check out some of my other fun maths videos as well, and do consider subscribing if you haven't already. Anyway, I'll catch you in the next one. Have a great day.